Hello, my name is Jennifer Morris. I'm a research scientist at the MIT Joint Program on the Science and Policy of Global Change. This talk for the MIT A+B Applied Energy Symposium falls under the B category of emerging technologies that could potentially play a significant role in energy systems in the second half of the century. The technology I'm focusing on today is bioelectricity with carbon capture and storage, or BECCS. BECCS is considered a negative emission technology. Like all plants, energy crops such as switchgrass or miscanthus absorb carbon dioxide as they grow. Typically, the carbon dioxide embedded in the biomass would be released when it's combusted to generate electricity. However, if the CO2 is instead captured and stored, this pathway of electricity generation results in negative emissions. The CO2 is removed from the atmosphere during the growing of the biomass feedstock, and those emissions are never released. This work sets out to explore the economics of BECCS technology in a 1.5 or 2 degrees Celsius world, which is what the Paris Agreement aims to achieve. This work was conducted along with the co-authors listed on the slide. In general, negative emission technologies are valuable in scenarios with strong mitigation targets, such as the 2C and 1.5C scenarios. In the IPCC 1.5C report, main emission technologies utilized in the scenarios with up to 20 gigatons of CO2 of negative emissions per year. However, land-based approaches such as BECCS or afforestation raise concerns about economic impacts, especially for food prices, as well as environmental impacts such as sustainable biomass, land use change, water availability, etc. The goal of this work is to quantify the potential scale of BECCS and its impact on the economy, considering technology and economics, but excluding consideration of aspects related to sustainability or political feasibility. We do this by integrating a BECCS technology into the MIT Economic Projection and Policy Analysis Model, or EPA. EPA is a multi-sector, multi-region general equilibrium model of the global economy designed to explore the evolution of economies, energy, and emissions. This work extends the literature by integrating all major components necessary for a comprehensive representation of BECCS. This includes land availability, crop production and transport, biomass conversion to electricity with CO2 capture, the transport and storage of the CO2, endogenous land use change, and direct and indirect land use change emissions. We explore the BECCS technology under the two policy scenarios. Both are designed as emission caps with a global carbon price starting in 2020, and they're designed to ensure that the global mean surface air temperature in the year 2100 does not exceed either 2 degrees Celsius above pre-industrial levels with a 66% probability or 1.5 degrees Celsius above pre-industrial levels with a 50% probability. This figure shows the reference or business as usual emissions, as well as the emissions under the two policy scenarios. First, we look at total primary energy use. Under the business as usual, 83% of total energy is fossil fuel based. Here is the primary energy use under the 1.5 and 2C scenarios without BECCS available. The 2C results are shown as solid bars and the 1.5C results as transparent bars. In these cases, total energy is cut dramatically. By 2100, it's reduced to just 33 to 38% of total energy under the BAU, business as usual. About 40% of that is fossil energy. When BECCS is available under these policy scenarios, the picture is very different. By 2100, the total energy ends up at just below BAU levels, with about 50% being fossil and 30 to 36% biomass. In these scenarios, biomass accounts for 320 to 390 exajoules in 2100. And with BECCS available, there's 3 times more fossil fuel use than when BECCS is not available. Most of the coal and the gas in these scenarios is accompanied by CCS. It's the emissions from the oil use that are being affected or that are being offset by BECCS. And you can see the increase in oil in these scenarios in the yellow. Looking at total electricity generation, we see that under policy without BECCS, the purple lines, electricity generation is significantly lower than in the business as usual. However, under policy when BECCS is available, the green lines, electricity generation continues to grow and even surpasses BAU levels. In those cases, 34 to 40% of the total generation mix is BECCS. The negative emissions from the technology lower its marginal operating cost, and at high enough carbon prices, the costs are lower than renewables and nuclear, which lowers the overall electricity price, encouraging more electricity use. We next look at total CO2 equivalent emissions, which we divide into non-CO2 greenhouse gases, fossil CO2, industrial process CO2, and land use CO2. Under business as usual, emissions continue to rise, dominated by fossil CO2. Without BECCS available, the 2C and 1.5C targets are achieved by significant emission reductions, about 86 to 90% reduction in fossil CO2, about 80% reduction in industrial process CO2, and 64 to 70% reductions in other GHGs. When BECCS is available, the same overall emission caps are met, but in a very different way. The negative emissions from BECCS reach 21 to 26 gigatons of CO2 per year by 2100, and a cumulative of 620 to over 1,000 gigatons of CO2 over the period from 2020 to 2100. These negative emissions make room for more fossil emissions, which are 3 times greater than in the scenarios without BECCS available. In terms of the regional distribution of where the BECCS is coming from, Africa is the dominant supplier as it has abundant land resources available. Looking at the global carbon price, there's a stark difference under the policies with versus without BECCS. Without BECCS, the purple lines, the carbon price rises dramatically throughout the century. However, when BECCS is available, the green lines, it effectively caps the carbon price at about $240 per ton CO2, which is an order of magnitude less than the price without BECCS. The carbon price raises the issue of, or raises the question of carbon permits as a source of revenue for BECCS versus electricity generation as a source of revenue. We performed a series of experiments to explore the contribution of each revenue source. We asked, what if BECCS receives no credit for its negative emissions, no CO2 permits? In this case, there's 0 BECCS deployment. We asked, what if the cost of BECCS is doubled? In this case, BECCS in 2100 decreases from 21 gigatons of CO2 under our base 2C scenario with BECCS to 13 gigatons of CO2 per year. So even though it is not at all competitive as an electricity generation technology, it still operates. Going one step further, we imagine a BAC technology or biological air capture, which is BECCS without the electricity production. In this case, BECCS decreases from 21 gigatons to 19 gigatons CO2 per year by 2100. So only a slight decrease if it is not producing electricity. And then to account for the fact that there are no costs related to electricity generation in the BAC technology, we make it 22% cheaper than the BECCS technology. And in this case, it's deployed back to the 21 gigatons per year by 2100. So this series of experiments shows that carbon permits are really driving the deployment of the technology, and the value of CO2 removal is far greater than the value of the electricity generation. Next, we look at the impact of BECCS on the overall cost of meeting the policies. Here, policy cost is defined as the percentage change in economy-wide consumption relative to consumption in the business as usual scenario. Without BECCS available, the purple lines, policy costs would be 13 to 19% losses in welfare. With BECCS available, the policy cost is limited to a 4 to 5% loss. So BECCS is significantly reducing the cost of meeting the long-term targets. So we've seen that BECCS can have economic benefits under policy, but what about the impact on land use change and agricultural commodity prices? Here I'm showing land use changes under the 2C and 1.5C targets with versus without BECCS. High level of BECCS deployment translates into substantial additional land use change. The 2C with BECCS results in an additional 490 million hectares in 2100, which is displacing mostly cropland and pasture land. The 1.5C with BECCS scenario results in an additional 650 million hectares and displaces more natural grassland and natural forest land than even the 2C scenario with BECCS. So a key question is, how do these land use changes affect food prices? Here I'm showing global food price indices with the price in 2015 normalized to 1. Under the BAU, food prices in 2100 end up at about 3% higher than 2015. This is due to the fact that the increase in demand driven by population and GDP growth is compensated by an increase in supply facilitated by agricultural land expansion and intensification. Under the 2C and 1.5C policy without BECCS, the purple lines, the 2100 food prices end up about 5 to 8% lower than BAU. This is driven by a decrease in total consumption compared to the business as usual scenario, leading to lower demand for primary goods such as energy and food under the policy. When BECCS is available under the policies, food prices increase and end up at about 0.6 to 1.5% higher than BAU in 2100. This is because meeting the 2C and 1.5C targets with BECCS increases the pressure on land, displacing cropland and pasture land for bioenergy production. And the downward price pressure from less demand for agricultural goods is offset by upward price pressure from increased land competition and land prices. However, overall, given the level of BECCS deployment, the impact on global food prices is quite limited to the less than 1.5%. And the same is true we find for other agricultural commodity prices such as crops and livestock. So to conclude with some findings and discussion, we find that BECCS can be a significant mitigation technology, particularly in the second half of the century. It not only lowers the carbon price and the policy costs, but it does cause significant land use change, but that only increases the food price by about 1.5%. There are many uncertainties that could limit the BECCS deployment to be less than what we find here. Of them is the availability of sustainable biomass, which was not considered in this work, as well as the available of geological storage sites, policy incentives, the development of a credible accounting and valuation system for negative emissions, and social assistance. Similarly, ecosystem impacts are also a concern, which were not considered, and whether or not there would be social acceptance of reductions in natural land was not considered and could limit deployment. However, we should note that the impacts can be mitigated by rules and regulations, so forests can be maintained for multiple purposes, for example. Finally, I would like to end by noting that all of the technical components for large-scale BECCS currently exist. Large biomass plants operate today, for example, the Drax Power Station in England, and CCS has been demonstrated at the million-ton scale at 2 coal-fired power plants. And there's actually a pilot CCS unit at the Drax station capturing 1 ton of CO2 per year. So this technology could be developed to play a significant role in the energy transition in the future. So with that, I conclude and thank you for your attention and hope you enjoy the rest of this symposium.